Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. In this video we're going to take a look at some important properties of definite integrals. In this video we're just going to take a few minutes and explain some properties of definite integrals here. There are three main new properties that are specific to definite integrals. And the first one we're going to take a look at here is called interval addition. And the properties of definite integrals, the three we're going to discuss here, they all make perfect sense if you actually just draw the picture of what this says. And if you recall, the definite integral has a direct connection to a graph. When we see over here in our definition the integral of f of x from a to b, we're describing the area under this curve, f of x, all the way from the lower bound a to the upper bound b. So this whole region in here, if we could determine that value by the fundamental theorem, then we would know what that is. But that area, whatever it is represented by the definite integral. And so what the interval addition says is that if you need to, and there are certain cases that we'll encounter where this is important, if you need to divide the interval from a to b up into some number of adjacent intervals, you can. So it's typically written this way: if there's some c value that lies between a and b, so let's just say on our sketch c is about right here, then we can divide the integral up into two chunks and say, okay, well let's do the integral from a to c, from the left end point of the whole region to this interior point c. That would be this much. And then to that we're going to add the integral of c to the right end point of the whole region b. And that would be this smaller region here on the right. So if you draw it and you look at what we're saying here, it makes perfect sense that if we would need to, we can break an integral up in specific places and integrate it in chunks as we go from a to b. Now for things like polynomials and continuous functions, you're not going to have a lot of call for that, but you should understand that this property exists, and there are a few cases that it's going to be needed. The absolute value in particular is one, and we'll put an example of that up soon. The second property is pretty basic. I like to call it the zero width property. I don't know if I'm just inventing that, but it makes sense. What it says is that the integral of f of x dx from a to a is 0. So in other words, if I'm doing an integral from a left end point a to itself, the sketch of it looks something like that, and it has no width to it. So there's no area under the curve at that point, and so the answer would be 0. So it's nice to just know that every now and again we encounter that. It's actually used in a proof of the fundamental theorem of calculus, and it also could be very easily proven by the fundamental theorem, because we could just say, well, whatever the antiderivative function is, capital F, the antiderivative of the upper bound a minus the antiderivative of the lower bound is the exact same quantity, and so that's proven to be 0. So it's just kind of a nice one to know. Pretty simple one. Call that the zero width. If you integrate a function from a number to itself, by definition that area is going to be 0. The third property of definite integrals is called reversal of limits, and what it states is that if you need to or wish to reverse the upper and lower limits on your integral, you can do so. You just have to multiply the entire integral by -1. Traditionally we like to have the lower number as the lower bound a and the upper value is the upper bound b, but that's not a rule. We don't have to do it that way. So the reason why this works, if you look at it, if we're describing the integral of f of x from a to b, definite integrals are often described as summation, and what we can think of, and in the proof of the fundamental theorem we see this, is that we're accumulating area as we step from left to right. So if I'm going from a to b, I'm adding up these little regions, and if a is less than b, my delta x value is going to be positive. And ultimately there I would get to the right endpoint and I'd have my total, and we can calculate that number by the fundamental theorem if we know the antiderivative. The reason why when you reverse limits you have to include the -1 here in front of your definite integral is because if I'm integrating from b to a, I'm working, in this case, from right to left. I'm working in the opposite direction than if the limits were reversed. So I'm calculating these areas, and what happens here is you end up getting negative values for these regions. Now in geometry, a negative area doesn't really make much sense, but it's a directed area. So if I'm going from right to left here, the delta x values are negative as I'm calculating these regions. So the magnitude of the area under the curve is going to be the same, but one's going to have a plus in front of it and one's going to have a minus in front of it. And so that's why the reversal of limits property is there. The only time you really encounter that and need to use it a lot is when you start getting into definite integrals that involve u substitution, and I'm sure we will encounter that at some point as well. It should be pointed out there are two other properties that most textbooks discuss as far as definite integrals. One of them is the constant multiple rule, and the other one is the sum and difference rule. Those two technically are properties of antiderivatives. They apply whether or not you have an indefinite integral or a definite integral. So although they're listed in most textbooks as properties of definite integrals, they're really properties of antiderivatives. These three are properties of definite integrals because if you go back and review them, they're all very tightly associated with the bounds of the integral. So that means they don't apply to the indefinite integral case. If you'd like to learn more about definite integrals or calculus in general, you can find more on my textbooks available for a nice price on Amazon. Don't forget to subscribe to the channel if you liked it. And until next time, I'm P. Clark.